Okay, ma'am. When should I start?
Or 2 minutes. Let me start the live streaming. Okay, just 2 minutes. Yes, Sahil, you can start. A warm welcome to everyone to the second day of our hackathon. Have a happy learning. Yes, you proceed, Sahil.
Good morning to one and all present here. I'll be presenting on the topic of RAID levels. So before starting, one should know what is a RAID. So RAID, also known as Redundant Array of Independent Disks, is a setup consisting of multiple disks, data storage disks. So having multiple disks allows the employment of various techniques like data striping, data mirroring, and parity. A RAID is a data storage technology that takes multiple physical disk drives components into a single logical unit. So RAIDs are designed for two purposes: improve performance and data redundancy. There are several different RAID configurations that have both upsides and downsides. So let's dive into the different types of RAID combinations, and we'll see which one is better for performance and redundancy. These will be the RAIDs that I'll be covering in this slides, and I'll start with RAID 0. So RAID 0 array includes 2 or more disk drives that provide data striping. This means that the data is evenly distributed across the disk drives in equally sized sections. The downside with RAID 0 is that they do not maintain redundant data, which means they offer no data protection to you. In an event of this failure, all of the data will be lost in this type of RAID. This type of RAID is actually never recommended. Only use this type of RAID if you're storing something that doesn't really require redundancy. RAID 0 is best used for storage that is non-critical but requires high-speed read and writes. Caching live stream video recording, video editing are common uses of RAID 0. And due to the speed and performance, disk striping without data redundancy may be used for temporary data. Moving on to RAID 1. So RAID 1 array consists of 2 drives minimum. In this configuration, one disk drive is mirror of the other, meaning that they both have high performance and they store the same data on them. The upside of this array is that the increased performance which boasts up to 2 times the read speed. But the write speed is only of the one disk. However, it comes with limiting the capacity of 50% of the total disk space. The mirroring in RAID 1 also has benefits for providing high availability of and rapid recovery. In an event of drive failure, the data would still be safe. Now moving on to RAID 10. Now from RAID 10, all the RAID uses a type of RAID controller. So if there are even number of hard disk drives, disk striping can be combined with disk mirroring to speed up performance and expand capacity by striping data across multiple sets of mirror drives. The combination is also called as RAID 10 or RAID 1 plus 0. RAID 10 array consists of 2 or more equally sized RAID 1 arrays. The data in RAID 10 array is both striped and mirrored. This gives you both a boost in performance as well as data protection. To implement RAID 10, you need at least 4 drives. You also need a disk controller that supports RAID. Now we'll move on to RAID 5. These type of RAIDs requires a minimum of 3 disks. For redundancy, this array uses data striping and parity, which also provides data protection and a performance boost. RAID 5 stores parity blocks on a stripe disk denoted by R here. Each stripe has its own dedicated parity block. RAID 5 can withstand the loss of one disk in the array. RAID 5 combines the performance of RAID 0 with the redundancy of RAID 1, but takes up a lot of storage space to do it, about 1/3 of the usable capacity. So basically, if you have 3 disks, 1 disk would be used for redundancy and other 2 will be used for data. The upside of that is that the parity data is error correcting redundancy that is designed to recreate the data if the device fails. Now I'll move on to the RAID 6. One second. RAID 6 array are also referred to as dual drive protection failure drives. This array uses data striping and parity data for redundancy. What sets this apart from RAID 5 is that it uses 2 independent sets of separately striped parity data. 2 independent parity computations must be used in order to provide protection against double disk failures. 2 different algorithms are employed to achieve this process. The upside of this setup is that you are extra protected. A RAID 6 array can recover from 2 simultaneous disk failures. Your maximum stripe size is also dependent on the number of disk drive in the array. The only downside of the RAID 6 is that extra parity slowed down the performance. Now I'll move on to the application of something like a RAID. Many of you might already know what is a NAS. It stands for Network Attached Storage. What it is a typical computer that stores data on internal or external hard disks. If the computer is connected to the network, it can share the data across its network on any device that is connected to the network. So in a recent trend, we are seeing many people making their own NASs for their home. So I would recommend using NAS plus RAID combination. It would be very helpful for both performance and data safety. I would also recommend using something like FreeNAS, which is an operating system for building your NASs, so that it's easy to implement your RAIDs, and you can easily set up your home theater or home system for this. So I'll end this presentation with a quick warning that RAID is not a backup. Here's one important caveat about RAID and backup. Although RAID writes data to 2 disks simultaneously, it is not a backup. If your operating system or software rather than the hard disk corrupts the data, the corrupted data is sent to both the disks and simultaneously corrupt both the drives. However, a backup is a copy of data which is stored somewhere else and is detached from the original data both in space and time. Backup is not corrupted unless you specifically back up corrupted data. In short, even if you use RAID, you must still use an effective backup software. I think I'll end with this part, and I'm extremely thankful for giving me this opportunity to present this. Thank you, ma'am.
Thank you, Sahil. It's a clear presentation. Thank you. Next team can start the presentation now. Who is the second team? Next team?
Ma'am, I'm Harsha.
Okay, Harsha. Start presenting.
1 second, ma'am. I just joined.
So during last day, we learned much about Flying's taxonomy, teaching about single instruction, single data and single instruction, multiple data with all streaming capabilities, and we have touched upon with a few quizzes as well. And one team has touched upon the pipelining concept, and they just started with handling on problem also. Since yesterday most of them started with Flying's taxonomy, I think today you guys might not touch it and you would have gone with the different topics. Arshita, are you ready?
Yes, ma'am. Is it visible?
Yes, it is visible. Proceed.
Yes, ma'am. I'll start. Good morning, everyone. I'm Harsha, and I'm going to talk about sawtooth wave generator in eSIM. So, what is a waveform? A waveform is a shape that represents change in amplitude with
Your
respect
voice is
to...
very feeble, Arsha. Can you keep your mic closer to your mouth?
Yes, ma'am. So
Can you
on the
increase your
x-axis
voice?
indicates the time, and on the y-axis it indicates the amplitude. Like for example, sine wave, square wave, triangular wave, sawtooth wave. So I am going to take sawtooth waveform and I am going to generate it in the eSIM simulator. So sawtooth waveform is a type of linear non-sinusoidal waveform, and it has different rise and fall time. So the difference between triangular wave and sawtooth wave is that this is symmetric and the rise time and the fall time is same, but in this one this is not the same. And this is a asymmetric triangular wave. The applications of sawtooth waveform in tone frequency generation and modulation, like time-based generators and pulse width modulation circuits. It is also used in music, like the sawtooth wave and square wave are like common starting points to create sound, and it is also used to generate the horizontal and vertical deflection signals in the CRT based television or monitor screen, which were the first television not used, but earlier it was used. It is also used in oscilloscopes and switch mode power supplies. So to generate this sawtooth wave in eSIM, I have used NA555 timer and 741 op-amp. So this is generated by integrating the square waves with unequal rise and fall time. So here we are going to use this timer IC and we are going to generate a asymmetric square wave, and then we are going to integrate it using the op-amp. This is just for explanation. So here the IC NE555 is wired as a stable multivibrator with unequal on and off time. So the resistor R1 and R2 and capacitor C2 sets the on and off time period, and the value of the components are so selected that the off time is less than 10% of the on time. So this is less and this one will be more. The asymmetric square wave is available at pin 3 of the IC, and for the stable multivibrator working, when the power supply is switched on, the capacitor C1 will start charging through R1 and R2, and when the voltage across C1 is above 2 by 3rd of the VCC, then the upper comparator inside this IC will swing to positive saturation. So this triggers the internal flip-flop, and this makes the output at pin 3 low. Now the capacitor C1 will start discharging through R2 into the pin 7 of the IC, and when the voltage across C1 will be less than 1/3 of the VCC, then the lower comparator inside this will again swing to positive saturation, and this again triggers the internal flip-flop. As a result, the output at the pin 3 will go low. This is repeated.
Arsha, your voice is not at all audible, Arsha. Kindly increase your voice.
Ma'am, is it visible, audible now?
Kindly raise your voice, ma. Thank you.
So this is repeated till we get a square wave at pin 3 of the NE555 IC. The asymmetric square wave obtained at output of this is integrated using the inverting active integrator, which I have made with op-amp IC 741. So resistors R3 and R4 set the gain of this integrator, and R4 in combination with R3 will set the bandwidth of this waveform, which I generate finally. Since the integrator is wired in inverting mode, the sawtooth waveform falls. Output is high and it rises when the timing output is low. So since the time is high, so as you can see, the fall is for a greater time and the rise is for less time. The on time and the off time is determined by R1, R2 and C1 using this formula. So as I already said, the R1, R2 and C1 determines the rise time and the fall time. So as we give the value for this, we will be getting corresponding graphs for corresponding square wave and corresponding sawtooth wave. This is the circuit which I used for recent simulation. The same as this one. So first we create the circuit in eSIM. Ma'am, is it visible?
Yes, it is visible. Proceed.
Yeah, so first we create the circuit in eSIM and then we will be converting it values and then we will simulate it. So as you can see, we get the waves. So this is the input wave. This is the wave at pin C, the label C, which is the trigger pin of the IC. And then this is the output 1, which is the square wave output we should get. And the output 2, where we should get the final sawtooth wave. So this is the input. This is the trigger pin. This is the square wave. And the final, which we should be getting. Now to plot the Python plot, we can select whichever we want to plot. So we will be plotting output 1 and output 2. So as you can see, this is the input, trigger pin and the square wave and the final sawtooth wave which we get. Thank you, ma'am.
Okay, thank you, Harsha. Hope you learned a new tool called eSIM. So
Yes,
whoever has presented yesterday, even yesterday, few has presented through eSIM. I believe and happy that you learned a new tool. Thank you so much. The next team can start. Who's the next team is going to present?
Yes, ma'am. Just 1 minute.
Okay.
Good morning, ma'am, and hello everyone. This is Sangramil Hazarika from the team quartet with the team code ARC14. Today we will be discussing on the topic magnetic and optical technologies. Me and my team members are Kunal, Ninad, Sahil, and Sahil. So coming to storage devices. What are storage devices? A storage device is any hardware device that is used for storing, porting, and extracting data files and objects. It can hold and store information both temporarily and permanently, and can be internal or external to a computer server or any several computing devices. Basically, the data files can be image files, text files, etc. The storage devices are used to store the data before and after a process by the computer. Different storage devices have different size and capacity. Also, storage devices differ on the basis of cost. So, what are magnetic storage devices? Magnetic storage device is one of the most affordable ways to store large amounts of data. Some of the examples are magnetic tape, floppy disks, and hard disk drives. Here, magnetic tape and floppy disks were not becoming recent trends. Hard disk drives are becoming recent trends because of some of the disadvantages of magnetic tape and floppy disks, which I will be discussing. Magnetic tape data storage is a system for storing digital information on a magnetic tape using digital recording. Magnetic storage or magnetic recording is the storage of data on a magnetized medium. Here in magnetic storage, we have three components: write head, read head, and medium. So what are magnetic disks? Magnetic disks are basically secondary memory which holds data and is covered with magnetic coating to hold information. So it stores programs and files in the form of tracks, spots, and sectors. These tracks, spots, and sectors will come into part of a construction, which we'll be discussing. And the polarized information, the polarization is represented by 1 and vice versa, and the direction is indicated by 0 here. And magnetic disks are less expensive than RAM, and as it is a secondary memory, so data access rate is slower than the main memory. And here in the magnetic disk, data can be updated, modified, deleted, etc. It also allows random access of data. These are the types of magnetic disk. What's the floppy disk is basically a soft magnetic disk. It's a thin magnetic disk sealed in a square plastic carrier. We have a floppy disk drive to read and write data from a floppy disk. And in floppy disks are portable because they can be removed from a disk drive, so they are portable. And these are the disadvantages of floppy disk compared to hard disk. Floppy disks are slower to access than hard disk and have less storage capacity. But one advantage is that the floppy disks are less expensive and also they are portable. So this floppy disk, also termed as floppies, comes in two basic sizes, namely 5/4. I conclude by saying the difference between magnetic tape and magnetic disk. Basically, magnetic tape is less frequently used. It was used in the earlier times. Now, recent trends is of hard disk, including consisting of magnetic disk, which is more frequently used. In magnetic tape, it is made up of plastic material coated with magnetized medium, a narrow strip. And in magnetic disk, it is basically a disk. Stator is basically a disk which is magnetized. Then magnetic tape, sequential access should be followed. In other words, in order to access data, we must follow a sequence process. For example, let's suppose you want to access the 5th song in a playlist. So we have to go right from the first song. We cannot randomly access the 5th song. But in magnetic disk, we can randomly access a particular song if you want. It means we can access data randomly. It provides random access of data. So since it provides sequential access, it's slower in data accessing, and magnetic disk is faster in data accessing because it provides random access. In magnetic tape, data cannot be updated, but in magnetic disk, data can be updated. In magnetic tape, it's less expensive, but in magnetic disk, it's more expensive. And the last disadvantage of magnetic tape is that it is more prone to corruption of data, but in magnetic disk, it is less prone to corruption of data. Now, my friend will be describing the construction part.
So, magnetic disk. Hello, I'm Minar. Magnetic disk, it is a thin and circular metal plate. It is coated with a thin magnetic film, usually on both the sides. Digital information is stored on a magnetic disk by magnetizing the process. Here is one image which I showed. Then the structure of the mechanical structure of the magnetic disk. The disk is circular plate metal. The rod connected to all metal plate is rotary drive. Rotary drive is continuously moving on a circular way. The disks are mounted on a rotary drive, right here shown in the diagram. Here the magnetized surface moves in a close proximity, that is near to each other, to magnetize the coil or head as shown in the figure. Then a read or write header. A read or write head consists of a magnetic yoke and the magnetic coil. Here shown in the image. Here's the wire like a coil, and here's the yoke. The digital information can be stored on the magnetic film by applying current to the magnetizing coil. That is, after passing current, magnetic field is generated using this field. Head can read or write on a circular plate. And this air gap in this image, this is useful to reduce the inductance. Then a layout of the magnetic disk. The concentric set of rings are generated due to the movement of the header, right? Here in the image I showed you. The data on the disk is organized in a concentric set of rings as shown in the diagram. This concentric set of rings are called the track, and the tracks are further divided into the sectors. Like here I mentioned S1, S2, S3. These are the sectors, and each sector stores a block of data which can be transferred to or from the disk. Then data bytes are stored serially on each track. Same number of bytes stored on each sector in a single track. To avoid that magnetic interference, like between the tracks, between the sectors, the two adjacent sectors, the gap is introduced between that, right? And the sector is the smallest unit that we can actually read in the hard drive. And storage capacity of tracks increases as we move from the innermost track to the outermost track. Then a header is initially at the start of any sector, and header recognizes that the start with some bit pattern. Like you should understand, like this is the start of sector, and at the end of each sector there is a checksum. Right? Checksum is to rectify and check the error. And basically, this is an important formula. Like, what is disk capacity? Disk capacity is number of platers into 2. 2 is for surface, right? And then tracks into sectors or into bytes. Usually we have number of plates, something 3 or 4, and thousands of tracks per plates, and some tens to hundreds of sectors per track, and some kilobytes of data. Then next, how data read and write in the magnetic field. This is very important. Here, due to magnetic field, the poles are generated, right? We already know it's North Pole and South Pole due to attraction and repulsion. Then red marked are South Pole, here I mentioned, and the blue marked are the North Pole, and the gray colored are unvisited, right? In the architecture, like it is already predefined that a North treat as 1 and South as 0. It may vary from architecture to architecture. Anyway, the bits are stored in 1 and 0 zone, right? So in this way, the data read or write on the disk. So now the next part, Sangram will explain about the usage.
So the current usage is that since much of audio and video production is moving to digital systems, so the use of hard disk is increasing. Digital tape and tape libraries are popular for the high capacity data storage of archives and backups. So here the floppy disk users have become nominal, which was used in older times, in older computer systems and software. Magnetic storage is also widely used in some specific applications such as bank checks and credit or debit cards. So now my friends will be talking on the topic optical technology.
Hello everyone, I am Sahil. Today I am going to discuss about optical disks. So secondary storage devices are broadly classified into 3 main categories: solid state storage devices, that is the USB drives or SSDs, and we have the optical storage devices, that is the CDs, DVDs and the Blu-ray discs, and lastly we have our traditional magnetic storage devices, that is the hard disk. So here each one of them has its own advantages and disadvantages. So depending on the work we are doing, we opt any one from these 3. So I'm going to discuss about optical disks and drives. So basically optical disks and drives were first developed in the late 1960s by James Russell. So, however, here we use the optical storage technique. So basically our data is stored in the digital format and laser beams are being used to access the data in the disk. The beams in the disk drive are being transmitted from the laser head, which is mounted on the optical disk drive, to the optical disk. In the optical disk, we can store more data and it has a much longer lifespan than our traditional magnetic storage devices. To use the optical disk on our laptops or desktops, we require optical disk drives. So some of the examples of optical disks are CDs, which was used quite earlier, and the modern day disc, which is this DVDs, and the Blu-ray discs, which are in trending now. So now let's discuss about the compact disc, that is the CDs. CDs are one of the optical discs which can store large videos, audios, and huge amount of data. To use CDs in a laptop or desktop, CD drive must be installed, which helps the computer to read the encoded data digitally from the CD. CD has the capacity to store the data from 650 to 700 MB. The key point here is that it uses a red laser beam to access the data. We usually see 3 types of CDs. First one we have is the CD-ROM, that is the CD read-only memory. Here, during the manufacturing of the disk itself, the data is being written on the CD, which cannot be modified later, but only can be read from the disk. The second one we have is the CD-R, that is the CD recordable. Here too, once the data is being written on the disk, cannot be modified, but can be read from the disk. But here the user has the feasibility of writing the data once in the disk, but in the CD-ROM, the manufacturer itself writes the data. So lastly, we have the CD-RW, that is the CD rewritable. Here the data can be read and written multiple times, so it is more convenient for the users to use. But to use CD rewritable disk, CD-RW drive is necessary. So now let's look at the DVD, that is the digital versatile disk or the digital video disk. So from the structure itself, you can very well see that it looks almost similar to the CD. Here we use the same technology as used in CD, that is the laser beam technology. But here the tracks in the DVDs are much closely spaced as compared to CD, and the data stored here is almost 6 times that of CD. So the data is approximately 4.7 GB to 17 GB. So here also the access speed to the data stored in the DVDs is also much faster than the CD. So now coming to the latest technology, Blu-ray disc. So Blu-ray disc can store high definition audios and videos. These are available as single layer disc, which can store 27 GB of data, and the dual layer disc, where we can store up to 54 GB of data. It uses blue laser beams, whereas in the CDs and DVDs we use red laser beams. The access speed of the data in these discs are much faster than CDs and DVDs.
Okay. So I will be talking about the conception of optical disc. These are the different layers. First layer is graphic layer. This is the layer where we see the company logos and other written stuff using pen pencil. And then comes the lacquer layer, which is used to prevent oxidation. That is this layer. Then comes the reflective layer that reflects the laser back. That is the read head laser. Then a polycarbonate disc layer, where the data is actually encoded using length and bits. Usually bits are 0 and lengths are 1, but it may vary according to the company. So before understanding the conception, we must know what is replication. Replication is the process of producing discs via methods that do not involve burning of blank CD, DVD or other discs. The latter is known as replication. The process in the making of optical discs. Explaining these 4 steps. First step is creation of glass master from the original master. Next step, creation of nickel stamper from the glass master. Next step is injection molding of polycarbonate substrate from a stamper. And the 4th step is metallizing and lacquering substrate to give rise to CD-DVD. That is, we add all the layers in the 4th step. And starting with the making, so it is you are made using replication, and cleaning with yellow light is necessary to protect light sensitive materials. Then glass master clean using brush and deionized water. Cleanliness is checked using surface analyzer. If it is not much clean, then it may be clean again. Then a photoresist is baked. Then master is selectively exposed to light, simultaneously exposed to resist removed using tools. And then thin coating of metal is applied to the master, making a negative of the master. That is something like a copy of the master. Then the negative is peeled in a thin layer of plastic. That is the step. Then the plastic protects the coating. A hole is also made in the center of the disc. So we see that our CD is almost going to be ready. Then the negative is now a stamper, a part of the mold that will be used for application. That is this. In this process, we get another glass master, which will again be used for manufacturing other discs. Then machine closes the mold and injects polycarbonate in the cavity. This forms the disc with data on it. Then this is then covered with thin layer of aluminium. That this is actually the reflective layer, so which reflects the laser beam in the computer. Then layer of varnish or lacquer is applied for preventing oxidation of aluminium layer. Then a recordable disc that is according to the type of disc, that is CD-R, CD-ROM and other type of disc. The different layers are added like dye layer, alloy layer. Then a few impressions like logo of company and all are printed. Then grooves are made on the recordable disc. And interesting fact is that the rainbow color on the spectrum which we see on the disc is due to grooves. Grooves are nothing but circular circular pattern or spiral pattern on the disk.
So now let's see the advantages of optical disk over magnetic disk. Here the storage capacity is also high. Optical disk cost per bit of storage is also low. Lifespan in optical disk is more than the magnetic disk. Data stability is also high in optical disk. In the optical disk, on the optical platter, a much smaller area is covered to store a bit of data as compared to the magnetic disk. So the storage of optical disk also increases. The magnetic disk has a high chance of being corrupted by the environment, whereas in the optical disk it doesn't. The read-write head in the optical disk is much close to the disk. In the magnetic disk is much close to the disk, so the chances of the disk being crashed with the disk is also high. Where in the optical disk, the head is much far from the disk, so the chances of crash is also low.
Okay, so basic difference between magnetic disk and optical disk. The first and main difference is magnetic disk is a fixed store device, whereas optical disk is portable as it is very light and small. And optical disk generates a better SNR ratio as compared to magnetic disk. The sample rate used in the magnetic disk is lower than used in the optical disk. And another important point is that in optical disk data is sequentially accessed, whereas in magnetic it is randomly accessed. Tracks in magnetic disk are generally circular, whereas in optical disk they can be constructed spirally or circular according to the needs. And optical disks allow mass replication. On the contrary, in the magnetic disk, only one disk is accessed at a time. The access time of a magnetic disk is lesser than the optical disk. And for understanding point 4, we can take the daily life example in C program of array and pointers, where array is sequentially accessed and pointers is accessed using address. Concept is different, but we can understand it using this point.
So the conclusion is that storage devices are getting smaller and holding more data as time passes by. Backup is very important for business and personal uses. You need a device that can hold all your data and be reliable at the same time. Also, everyone has their own needs and preferences. So these are the references. I hope you enjoyed this learning. Thank you.
Thank you.
Good team. It's a neat presentation talking about the complete structure of magnetic disk. Good job. Thank you. Next team can take.
Thank you, ma'am.
Thank you, dears. Thank you. Who's the next team?
Ma'am, can you leave, right?
Yes, you can leave and join the live and start voting. Okay.
Thank you.
Okay. Thank you.
Hello, ma'am.
Yes, Dharnesh, your team.
Yes, ma'am. Yeah.
Okay.
I'm audible, ma'am. Right?
Yes, you're audible.
Okay. Yeah. So, good morning, everyone. I'm Dharnesh, and today I'm going to give you a brief introduction on the concept of pipelining and a little on its hazards. Believe me, guys, this is going to be very interesting, and in fact, you will feel like how did even computers existed without the concept of pipelining, but they did once actually. So the first and foremost question is, what is pipelining? And now this is the textbook definition of the pipelining, and pipelining is basically a technique where multiple instructions are overlapped during the execution. Now why they are overlapping, I'll just let you know soon. And don't worry if you didn't understand the terms inside the definition, I'll surely make you understand by the end of the presentation. So, okay, basically the thing called multitasking is very much essential, and this is how it is achieved actually, and it is done when the pipeline is divided into stages, and these stages are connected with one another in the form of a pipe-like structure. So that is why it is called pipelining basically, but it just forms a pipe-like structure, and that's why it is called pipelining simply. And the instructions enter from one end and exit from the other end, just like how it does in a pipe. And most important thing to mention is that we don't actually add new hardware to the system, but we actually rearrange the existing ones to increase the performance of our system. Okay, so to understand the advantage and what difference did pipeline actually created, you first need to understand how it used to get executed, like once upon a time before the pipelining concept was actually introduced. Let's imagine you have a processor with 4 cores inside it, and I know it has more processor. Just for the ease of understanding, I've given like this, and just take my case. presently I am generating the audio file, and if I open my camera, it generates a video file, and I'm sharing my screen, so it generates a screen file. So my processor should basically process three of them at the same time and then transmit it in order to like only then you will understand what I am saying, and everything will be synchronized. But once upon a time, how it was actually done was that they are simply made in a form of thread by the control unit, and then they are sent to the processor, and processor simply used to process one after another. And of course, this has its advantages, and basically like this doesn't have any hazards, so it's completely safe. And but the thing is that in the real world, simultaneously a lot of data is formed, and this kind of method will not actually allow the applications to experience the full potential of your processor, because nowadays the processors are way more powerful, and if you use this kind of method, if the files or applications really require the power of processor, you literally can't access it. Like at any point of time, two or more processors will be working, and other processors will be staying idle, and they will be used only when the application is a very high end application. Other than that, it will not, they are staying idle throughout the time. So now how it is arranged is that it is arranged in this fashion. Now in the physical hardware, this you can't see this kind of arrangement, but you simply change the connections. So the orange color ones are the combinational circuit, or basically the processors or CPUs, and the green color ones are the latches which store the intermediate results. They even existed in the usual system also, but using pipelining, the difference which got happened is that these files, they are not arranged like this. I have done this just for making you understand. The files are basically divided, and like basically the files or the program data is basically divided into 4 equal parts, or basically depending upon the number of processors you have. So when they are divided, these are further known as the fetch cycle, decode cycle, execution cycle. Like they're not simply divided; they belong to various cycles. Okay, so the first processor where the first file enters, like being programmers, whenever we program something, we assume that the first line is getting executed first, and then the second line is getting executed. But this in this process, we execute multiple instructions. So how do we do that basically? See, because if you don't execute the first line and if you start executing the second line, definitely it will be erroneous, and if at all error happens in this stage of execution, it will literally lead to the hanging of the system. So we should never let this happen. So, but still we have to do multitasking. This thing is basically achieved by the following. I will show you the animation, and I guess that would be clear enough to you. So basically, initially only the input processor will be working. This will only exist for some microseconds of time, and it will process and it will store the intermediate results inside the latch. Okay, and once it is stored inside the latch, this latch will only provide this data to the next processor. The before processor, like the first one, the input processor will not be able to access the latch. It can just output the data, but it can't take data from it. Okay, so once it is done, the intermediate results are used by the second processor, and the first processor will start to process the next file. So like this, see, now even just in the second stage of processing, you can see that both the processors are working on 2 different tasks, and everything goes fine basically. And in this, after this stage is completed, the first latch will store the video intermediate results, and the second latch will store the audio intermediate results. Okay, so once this is done, the next file is taken. So basically, in the next stage of processing, all the processors will be working, and they will be working on different files. So this actually ensures that the processors are being used and the resources are being used completely to use the potential of the computer basically, because without this you literally can't experience the power. So some of the advantages is that it enables the multitasking. Of course, you can see now it is processing screen, video, and audio at the same time. Resources are better used because you actually equally partition. This is done by the control unit basically, and you can design a faster ALU. So now you can sense the full potential of your system. You can design a faster ALU, and you can experience it. Okay, and then it will increase the number of pipelines. Actually, we don't have only one single pipeline. Yeah, I didn't explain you what is pipeline and what are stages. So basically, the first cycle when it took this is the first stage of execution, and this is the second stage, and this is third stage. Okay, now they are called overlapping because in first stage, see, the instructions are basically overlapping on one another, but they are not, clashing with one another. So this is called overlapping, and don't confuse with the pipeline. This audio, the way the files are arranged is not actually pipeline, but the pipeline is actually formed from input register to output register. If you see, the processor takes the data and puts it into latch, and latch takes the data and puts it into the other processor. So this actually forms a pipe-like structure, right? But at one processor, it is actually taking the data, and other processor, it is actually giving out the data. So the path which the data takes, actually looks like a pipe. So that is why this is actually called pipelining. I guess this was like very clear for you, and yeah, that's all about pipelining basically. So this is how we ensure that multitasking is done in our computers, and you don't execute one instruction. Like we have this kind of misconception, like how are we executing multiple instructions of multiple processes at the same time. So basically it is not clashing, and like it is not erroneous, but still this hazard exists, and this is schematic diagram. These are like the clocks are not exactly synchronized with the processors. They are partially synchronized because latches has to be very fast. They're like the memory devices which are very fast, which has very fast read and write speed basically. And the combinational circuit, it must be like it must be way faster than this one. Like you don't need a latch which need to be as fast as your combinational circuit. A combinational circuit will have different clock cycle, and it is synchronous. All the combinational circuits, like the S1 thing, S1, S2, S3, they are the combinational circuits, and they are all synchronized, and the latches are all synchronized basically. And coming to the part of hazards, they are basically categorized into three types of hazards. One is structural hazards, and they occur when two instructions of a process require the same hardware. Like basically, for example, when you have an input instruction and you are taking a very huge input, or you have an output instruction like print instruction basically, you have a lot of output, and the problem here is that your latch cannot store a lot of data. It can just store the the general purpose register state and the carry flag, like all the flag register state, status word register state, and it stores the register state, and it has very less memory to store the addresses, like where the particular data which is taken or data to be given as output is there. Like basically this occurs when two or more instructions require the same hardware, like kind of input instructions and printing instructions. It can't store a lot of address to take from that particular memory and send it to the output device basically. So second thing is data hazards, and they occur when the instruction from a process requires the data from the other instruction. I have said like it is actually the parts which are divided are like fetch cycle, decode cycle, and stuff. Just imagine when we are writing a normal C program, we at the starting phase we will basically include the libraries, and then we will directly start programming. So just imagine if the including of library thing is categorized as one process, and like executing your instructions are taken as second process. So while the first, like imagine you have 4 libraries. In the first stage, you have included one library, and immediately after that, the second library will be included, and the first, the input register will start to execute the codes which are coded by us. So if at all the first line itself had the functions from the 4th library, which like in that stage that will not be included yet, but this will actually lead to a hazard, like an error, like your system basically don't know what the function is, because though you have included the library, it is not being executed yet. So this is a kind of data hazard. And lastly, the control hazard. I'll just hide this one. Yeah. Control hazard actually occurs when there occurs a delay in fetching of instructions and making decisions. These have basically happened due to the control unit. When you have basically if you control the control unit rightly, it takes more time, and but it can actually resolve the above two hazards. But the thing is that if at all it makes delay in fetching the instructions or making decisions in the control flow, like how the data is being separated for various processors to process the data, any delay, even it is just a matter of microseconds. So if any delay in microseconds happen, it literally leads to the hanging of your system, and you literally, like every computer science student, I'm sure, has experienced it one or other time, while programming. Basically, it hangs up, and we literally don't have any control on the system, like why it's happening, and we don't understand what's wrong with the system, right? So thanks to the advanced systems like the present stage computers, we have multiple pipelines which actually detect this kind of they'll check, while executing itself, they check whether the other threads are moving or not, and if at all they're moving, they take steps, because nowadays if at all your application hangs up, it literally not lead to your overall operating system hang up, right? It simply says that the particular application is not responding, and then it will simply close it. And these all are the resolving techniques which I'm not covering, because this was meant to be the introduction of pipelining. So I guess it's clear for you guys. Thank you for listening, watching, and bearing with me. Yeah.
Thank you, Dharnesh. It's a neat and clear presentation about pipelining. Hope our students would have learned about pipelining and the various hazards. Thank you so much. Next team can take the lead. Yes, who is going to present next? Laura Shiny, you're going to present? You asked me in the chat?
Yes, ma'am. I can go if the other teams are okay. Can I go, ma'am?
Yes. Shall I ask Shiny to take the lead? Yes, we proceed. There is no response from the audience.
Yes, ma'am. Sure. Ma'am, is my screen visible?
Yes, dear, it's visible.
Yes. Okay. So, hello, you guys. Sorry if I scream in here. Maybe I'm just a tad bit enthusiastic. We are Geeks in Glasses, and this is my team. We have Thon and Ben.
Hi.
Tracy.
Hey guys.
Andra.
Hello.
And myself, Laura. And we're really happy to be here. So the topic we chose to talk about today is multiprocessor architecture, an overview of shared memory architecture and distributed memory architecture. Before we go into detail, I'd like to explain what parallel computing is. In the simplest sense, parallel computing is a simultaneous use of multiple compute resources to solve a computational problem. A problem is broken down into discrete parts that can be solved concurrently, which means basically a problem is divided into smaller parts and they process simultaneously at the same time. An overall control and coordination mechanism is employed. Instructions from each part is executed simultaneously on different processors. As you can see from the image, there are different processes running at the same time, and each instruction is divided into smaller instructions. This is an effective technology in modern computers to meet the higher demand for higher performance. It is lower in cost, and it gives accurate results in real-time applications, which is not possible with serial computing. Parallel computer memory architecture can be divided into two: shared memory architecture and distributed memory architecture. We all know that when there are two opinions, there's always a debate over which one is better than which one. So dare I say we have a debate between my teammates. We have Antra Devraju representing shared memory architecture, and the stage is all yours.
Hi guys. So I'll give you a brief introduction about what shared memory architecture is. So in shared memory architecture, the entire memory, that is the main memory and the disk, is shared by all the processors. In this, the memory that may be simultaneously used and accessed by multiple processors to provide communication among them or to avoid redundant copies. If you can see the picture, we'll realize that a fast interconnection network, which is the high-speed bus or the cross-bus switch, allows any processor to access any part of the memory in parallel. Because of this, each interface can run at full bandwidth at all times, so overall fabric bandwidth is really high. Shared memory architecture is based on symmetric multiprocessors. There are only point-to-point connection between the devices and the shared memory, somewhat easing the board design and layout issues. If we try to understand this with a real-life example, consider an office, and in a meeting, if people are presenting and they're using the whiteboard, all of the people who are presenting will use the whiteboard. So the whiteboard is like the shared memory over there, and the people are like the processors using it. With shared memory, the data is only copied twice from the input file into the shared memory and from the shared memory to the output file. It provides a way by letting two or more processors share a memory segment. This is widely used, and our everyday laptops and all our PCs follow this method. They are relatively easy to program. It is easy to deal with load processing because all the processors and memories are under the control of a single operating system. It is very efficient as the processors can communicate via the main memory, and because they have a single view of the data, the communication becomes really faster as the access is to the same location. It is less expensive and it is easier to use. All CPU It is highly used in DBMS porting also because it uses intra and inter-query parallelism, and it is used in parallel database systems, prototypes, and products.
Okay, Indra, you told a lot about the advantages of shared memory. But what about their disadvantages? You know, one of the biggest problem in this type of architecture is that all the processors that are using the shared memory model needs to make sure that they are not writing to the same memory location. What will happen if they write to the same memory location? We will lose some of the data that we want to keep instead of keeping every data. Shared memory model may create problems such as synchronization and memory protection that need to be addressed. If the memory space is not enough, what if the memory space is not enough? If the memory space is not enough, the processors have to wait before they can use the memory after other processors using the same memory finish the operation that they are doing and free up the slot. One of the biggest disadvantages is the lack of scalability between memory and CPUs. You said in shared memory architecture, many processors are using the same shared memory parallelly. But what if we add more and more CPUs together? So adding more CPUs can geometrically increase traffic on shared memory. It becomes increasingly difficult and expensive to design and produce shared memory machines with ever-increasing number of processors. The reliability and expandability is also another problem. A memory component or any processor failure can affect the whole system. So, Andra, I think shared memory is not that good when it comes to the multiprocessor architecture.
Oh, you guys, can you feel the heat? The debate is just heating up. Next to represent distributed memory architecture, we have RISC.
Thank you, Laura. Well, hey guys, I'm Priyasi. My friend Antra did tell some really good points about shared memory architecture. But let me tell you, my friend,
Wake up, open your eyes, because we are living in the world of supercomputers. You got it right, my friends. Supercomputers use distributed memory architecture. Now, before going on to the why, let me tell you what distributed memory architecture is. So, distributed memory architecture has multiple processors, each processor having its own memory. Laura, please go to the next slide. Thank you. So each processor has its own memory. Hence, all the tasks performed by the processor work on the data present in the local memory. But in case a processor needs data that's present in another processor, communication occurs between them. The data which is present in another processor is called as remote data. Communication occurs by using input-output instructions. So a processor first writes a request, this request is read by another processor. That processor, according to the request, fetches data from its local memory and then places in the interconnection device. So here topology does play a role because we can decide how the processors are connected and how much wire is actually required. Now, moving on to the advantages. Distributed memory architecture is easier to build. Can you see the next point, no overcrowding? Now imagine, as my friend Antra said, we can have a whiteboard in a meeting. I really can't imagine all of them rushing to the whiteboard to write something. Imagining the CEO's position and face is like really scary. It just avoids overcrowding. The distributed memory architecture avoids overcrowding, and this way the chaos is also avoided. And as my friend Thiruman rightly said, multiprocessors can be added easily. That's not the case in shared memory architecture. Here, we can add how many of our multiprocessors we want. And the best point is, when one node fails, it does not lead to the failure of the entire system. It's very unlikely. And in case of shared memory architecture, if the main memory fails, all the nodes fail. And that is not reliable. But here, all the nodes, they work on their own. They work independently. So even if one node fails, we can rely on it because the others are full on working.
Okay. Tracy, it's all good and well, but you said it's easier to build, but is it easier to use? Distributed memory is very, very hard to use because we need to communicate between different processors instead of sharing the same memory. So whenever a processor needs data from another processor's operation, it needs to fetch that data from that processor's memory. So in order to do that, it needs to send the instruction to fetch, which is more difficult than just loading and storing a data. And in this kind of memory architecture needs a lot of copies of operating systems. The updates must be maintained in all the systems, tending to increase the expenses. In case of large amount of data, decisions on splitting it have to be made. When you say that various processors have to communicate, the major problem is latency. This kind of communication leads to higher latency for intra-node communications, which will also mean that they also need bandwidth to actually handle communication. So, finally, I don't think that shared memory, it doesn't come to whether shared memory is better or distributed memory is better. Shared memory architecture is better when it comes to everyday devices and which are less expensive and are needed by ordinary citizens like us, like our mobile phones, PCs and laptops. And it's harder to build, but always easier to use, and it's less expensive. But on the other hand, distributed memory is easier to build, but harder to use, which is not very user-friendly for a commercial use. But they are needed to handle supercomputing. So I say that it all depends on our need. If you are an ordinary citizen looking for a normal device, we will always go for a laptop, which uses a shared memory architecture like SMPs and stuff. But when it comes to supercomputers which are used in space stations and governments, they need to go for the distributed memory architecture because they will have hundreds and thousands of processors which need to communicate between each other instead of using a shared memory.
Okay, my friends, I think that brings us to the conclusion of today's discussion debate. Just as in life where there's no black or white and everything is gray, here also, I don't think we can say one thing is better than the other. It's just everything depends upon its use and where they want to be used. So hope you all had fun, learned something new. We are just scratched the surface. You can go learn more about these stuff. And so hope you guys enjoyed. Thank you.
Thank you, team. Thank you so much. Your confidence in the concept shows how depth you learned the concept. It's really happy to visualize these things. Thank you so much. Thank you, dears. Thank you. Next team.
Ma'am, R17.
Yes, proceed.
Ma'am, can we leave the meeting?
Yes, you can leave the meeting. You join the live and vote for the attendance, dears. Okay. Even you can vote for yourself also. Thank you.
Excuse me, ma'am.
Yes.
Excuse me, ma'am.
Yes,
Ma'am, we are team 16, ma'am, so we wanted to present.
Okay, Arjun, proceed.
No, ma'am, but Arun started presenting.
Arun, you have class now?
10 o'clock network class I have.
Okay. Then Arjun...
Ma'am, we are Kanchana ma'am students, ma'am.
Then we can do later. Yes. Kanchana ma'am students can do later. I got permission from her. Okay, thank you.
Okay, ma'am. So, ma'am, can we do after this, ma'am?
Yes, after this, just do.
Okay, thank you. Ma'am, shall we start?
Yes. Start, Arun.
Good morning, everyone. This is Team Wizards at Work, Arc 17. I'm Shreya, and my teammates are Arun and Rahul. Today, we will be talking on magnetic disks and optical storage technology. So what is a magnetic disk? A magnetic disk is a storage device that is used to write, rewrite, and access data. It has digital information stored in the form of microscopic magnetized regions. There are basically two types of magnetic disks, and they are floppy disks and hard disks. Talking about the structure of the magnetic disk, it has various layers stacked above each other, and they are called as platters. They are generally about 1 to 4 in a magnetic disk. Both the surfaces of the platters are used to contain data. Each platter is made up of concentric circles called tracks, and again these tracks are divided into sectors. A cylinder is defined as a collection of tracks at a particular radius in all platters. Okay, so the disk capacity is calculated by number of platters into 2, which is the number of surfaces, and this is multiplied by the number of tracks per surface, multiplied by number of sectors per track, and number of bytes per sector. So, so the number of bytes per sector is in the range of thousands, and there are about 100 sectors per track and thousands of tracks per surface. So how do these read-write operations occur? An arm assembly will be pointing the read-write head to move forward and backward along the radius of the platter. Each surface will have its own read-write head. There is a spindle, which is the axis of the whole disk, which revolves the platters and is controlled by the read-write unit of the operating system. The rotation causes the required sector of the track to come under the head, and the data is read. So this is the speed of the disk is measured by 2 parts. One is the transfer rate. It is the rate at which data moves from the disk to the computer, and the second is the random access time. It is the sum of seek time and rotational latency, which is given in the further slides. So the total disk access time will be seek time plus rotational latency plus transfer time. So the seek time is the time required to move along the radius to reach the track. Rotational latency will be the time taken to move to the desired sector, and transfer time is the time required to transfer the data, and it depends on the size of data to be transferred. There are other factors which affect the disk performance. One will be the controller overhead. This is the overhead imposed by the disk controller. And the next thing is the queuing delay, is the time spent for the disk to become free. Next, Alan will be presenting.
Optical storage technology. Optical storage devices are electronic storage medium that uses low power laser beams to record and retrieve digital data, that is binary data. In optical storage, a laser beam encodes digital data onto an optical or laser disc in the form of tiny pits arranged in a spiral track on the disc surface. A low-power laser scanner is used to read these pits with variations in the of reflected light from the pits being converted into electrical signals. This technology is used in compact disc CD-ROMs, which can store text and images as well as sound, read once, write many discs, which is a type of disk that can be written on once and read any number of times, and in newer discs that are totally rewritable. Next slide. Now let me talk about CD-ROM. CD-ROM stands for Compact Disk Read-Only Memory. A CD-ROM is an optical disk and contains data that can only be read. Data can't be written or erased from a CD-ROM. A CD-ROM was basically used to store audios, still videos, pictures, animated graphics, as well as full motion videos. 3 layers. CD-ROM has transparent substrate made of clear polycarbonate plastic on its base. The base is coated with highly reflective material, which is usually aluminum, and this reflecting layer stores data. On the reflecting layer, there is a protective coating of clear lacquer. A CD-ROM can store about 650 megabytes of data, which is roughly some 3 lakh typewritten pages. In a CD-ROM, data is stored as bits. It is read by a reflecting laser on the bottom of the disk. A CD-ROM has a constant packing density where the data track is approximately 0.5 microns wide, a minimum of 0.83 microns long, and 125 nanometers high, with 1.6 microns gap separating one track from the next. With a constant linear velocity of 1.2 meter per second and the track being 5.27 kilometer long, the track length 5,270 meters divided by the constant linear velocity 1.2 meter per second gives 4,391 seconds, which is 73.2 minutes of storage time of an audio file. Next slide. Now let me talk about the working principle of a CD-ROM. The information to be stored is represented by binary numbers. This information is stored on the metal layer. The data is represented using bits, which represent binary 1, and spaces between bits is called LAN, which is the binary 0. A laser beam is used to read the data from the disk. The disk moves inside a CD-ROM drive at very high RPM. A laser is shown onto the reflective surface of the disk to read the pattern of pits and lines. The depth of the pits is approximately 1/4 to 1/6 of the wavelength of laser light that is used to read the disk. The laser rays reflected by the pits and the lines have a path difference of half the wavelength. It leads to destructive interference, that is, the two rays cancel each other and hence no reflected ray is resulted. This represents a binary 1. When the two rays are reflected either by pit or by line alone, the path difference is 0. Hence, no destructive interference occurs and it represents 0. In short, we get 1 at the edge of pits and 0 elsewhere. Next slide. Talking about the advantages of CD-ROM, they are small and portable and are very cheap to produce. Most computers can read CDs. If there is no CD drive, a DVD drive can usually read them. They are fairly fast in accessing the data. They are quicker than magnetic tapes. Talking about its disadvantages, CD-ROMs are fairly fragile and easy to snap or scratch. They have smaller storage capacity than a hard drive or DVD, and they are slower to access than the hard disk. Now I would like to call Rahul Reddy to deliver more about types of optical storage devices.
Next slide. Okay, now I'll talk about CD-ROM. It is made up of a reflective metal disc with a layer of dye on top, which is nothing but polycarbonate. Once data stored in CD-R cannot be erased. After storing the data, the CD acts as read-only memory. CD-R is more compatible and cheaper than CD read and write. It has more storage capacity of minimum 650 MB, and all CD players, that is older and newer, can read CD-R. Next slide. Now, coming to CD read write. It is also made up of a reflective metal disc, but it has a special metal on top. This special metal is nothing but an alloy with a polycrystalline structure comprising of silver, indium, antimony, and tellurium. Data stored can be rewritten multiple times. After storing the data, the CD acts as read and write itself. This is one of the most expensive CDs ever. It is best suited for data transfer, and it has a storage capacity of minimum 700 MB. Older CD players cannot read CD read and write. Next slide. Now, coming to DVD. DVD stands for Digital Versatile Disc. It is one of the digital optical disc storage format. A DVD disc has several layers made up of polycarbonate plastic. On an average, each layer holds up to 4.7 GB of data. Data on a DVD is also encoded in the form of small pits and bumps in the track of the disc. And on an average, it has a storage capacity of up to 17 GB. Next slide. Now, talking about the physical formats of DVD. There are 5 physical formats. The first one is DVD video. It is used to store motion picture. The second one is DVD audio. It is used to store only audio, and it is similar to the CD audio. The third one is DVD read. It is also similar to the CD read, where data can only be written once. The fourth one is DVD-ROM, read-only memory, and it is suitable for storing data that doesn't need to be updated frequently. And the final one is DVD-RAM, random access memory. It is suitable for storing data that needs to be updated frequently. And one more important thing is that DVD-RAM drivers have the ability to read DVD-ROM disks. But a DVD-ROM drive cannot read a DVD-RAM disk because data is stored in an optical cartridge. Next slide. Now, I'll talk about the pros and cons of DVD. First, let me talk about the pros. It can store large amount of data and it is completely heat resistant and durable. It doesn't transmit virus. And talking about the cons, DVDs are not fully supported by HD TV. And there is no single standard of a DVD. And the most important thing, the most important disadvantage of a DVD is that DVD players can read CDs, but CD players cannot read DVDs. Next slide. Now, I'll talk about the pros and cons of the optical storage. The pros is that it provides mass storage capacity and is very cheap. It has high data stability and can be reused sometimes. And the cons is that some older computers do not read the disk, so they require special drive to read and write. And when compared to other storage types, like flash drives or hard disk, it has less disk capacity. Thank you, and kindly vote for us.
Thank you, team, for giving us the idea about all your magnetic disk and optical. Thank you so much. Next, Arjun, you can take the lead.
Yes, ma'am. Yes, ma'am. Thank you. Ma'am, is the screen visible?
Yes, it is visible.
Okay, ma'am. Thank you, ma'am. We'll start the presentation now.
Yes.
Now, okay. Our topic is pipelining and computer architecture, and it's presented by Team 16, or also known as Speed. And now, you might be wondering why our team name is Speed. So, by the end of this presentation, you'll clearly understand the full potential of pipelining and why our team name is Speed. Now, our group members consist of Yash Mittal, myself, that is Arjun, Jerash, and Achintya Kumar. Now, Jarash will be telling you about or giving an introduction on what pipelining is.
Am I audible?
Yes, Jarash. Yes, Jarash.
So pipelining, before getting into what exactly pipelining is, I want to give a context or a background of why pipelining was introduced in the first place. So there is a law in computer science known as the Moore's law, stating that the computers in future generations would be smaller in size and the speed and the performance of the computer will increase due to the development in transistor. So right now we are living in a quantum computers, supercomputers with very high speed processors. So we are actually lucky. But if we see why when the pipelining architecture or this concept was introduced, it was back in like 30 to 40 years back, 1980s and 1970s, when we had a very huge processors, so which had very big delays and everything. And one thing that I think that we all like have a problem is basically a statement that we say about computers is that whenever we get a delay or lag, that processor is bad, or the processor is slow, or the speed is very bad, or something like that. So that is one of the specs that we always look forward to. So that is why this pipelining, this idea came into existence so that we can increase the speed and the performance of CPU. So the two ideas that the computer scientists had at that time was introducing faster circuits. And the second notion that they had was like arranging the hardware such that more than one operation can be performed at the same time. So if we look at these two notions, the first one was rejected because there is a limit to which we can make the hardware fast enough by introducing the faster circuits. The problem with this is because the faster circuits which would be implemented would be very complicated, and the second is they would be very costly. So finance is something that always bounces technology or something. That's why they went with the second notion, like saying that hardware we can implement, like we can have a simultaneous operation of instruction. So this is the basic idea of pipelining. So yeah, we'll go to the next slide. Arjun. Yeah. So here Dhruv is saying about the pipeline. So he is telling what pipeline is, and when he comes to the last statement that an instruction can be start before the previous one completes, he also gets confused. So let's understand what exactly pipelining means and how this architecture works through a video.
Sure.
Arjun, is the audio full for the video?
I'm actually using the headphones, so you might not be able to hear it because Google Meet doesn't have the option of sharing audio apparently. Should I remove my headphones and run with the speaker? Or
speaker, I guess.
Yeah. Okay. Fine.
Yeah. No, I don't think so. Okay, anyways, I will explain the video then. If you can put it to the start, I will just explain what exactly is happening. I'm really sorry for the inconvenience, but yeah.
No issues. Arjun, you share this PPT, I will share to them, okay? No issues, thank you.
Yes, ma'am.
Later on you share this, I will share to them for the better learning.
Okay.
Thank you. Now you proceed.
We'll go back to the presentation.
Okay, fine. Yeah. Okay. Tell me where to pause and I'll pause it.
Oh yeah. So basically what's happening here, the process is building a car. So if you see a normal, in a non-pipeline architecture, if we do this, it takes 24 hours to build a car and deploy it on the road. So the throughput here is 1 car per 24 hours. So what divide this task into 3 different tasks. So that is like engine, body and paint. So the engine team will create the engine for the car, and the body team will create the outside metal surfaces for the car, and the paint team will paint it. So what happens if you see the first 8 hours, an engine is built and it is put into the second phase, that is the body phase. So in the in the 16th hour, if you see, we have two processes that is working together. So that is what the main advantage of pipeline processes is. That in each, all the phases will work simultaneously and will use all the resources. So there is no wastage of resources that happens during a pipeline architecture. And two main thing we can see in a pipeline architecture is that there is pipeline architecture starts at the filling phase and the draining phase. So filling phase is basically in the starting 8 hours, if you see, only first phase is working and the other two phases are in the inactive state because they didn't get any output from the first phase. So for first 8 hours, it's a filling phase so that the entire pipeline starts to be active. And in the end, the same reverse order happens for draining. So the last part, the engine will be made and then the engine phase will get deactivated and then the body phase will happen and then this will happen, and the same similar architecture is used in the processors. So what each of the instructions will be simultaneously executed and they will be simultaneously fetched and decoded and executed. So thus we will save time. So if you see now non-pipeline architecture, the frequency that we get is 333 megahertz. And if we go to the pipeline architecture, the next, we will go for go ahead little bit. We'll come. Here we get a 1 gigahertz. So that is a basic advantage. The speed increases drastically in a pipeline version. We'll share this video after. A little bit more clarity we'll get about what pipeline is. Let's go back to the presentation.
Yeah, fine. Okay.
Yeah, so what exactly pipelining is the formal definition that we can give is a process of arrangement of hardware elements of the CPU such that its overall performance is increased. Simultaneous execution of more than one instruction takes place in the pipeline processor. So this was repeated in that video. Next slide. So a design of a basic pipeline is like we have two ends, the input end and the output end, and there are multiple stages in between. 3 stages. One was the engine phase, second was the body, and then the paint phase. So in the similar manner in processors also we have, which I will be discussing in the further slides. So there are also interface registers that takes this input and stores them so that it can be the input of the next phase. And all these stages of pipeline along with the interface registers are controlled by a common clock cycle. So in one clock cycle, you will see that multiple instructions are being get executed due to this architecture. Let's go to the next slide. Yeah. So now in a non-pipeline architecture, what happens is we have period. There is a read instruction memory, there is a read register file, then there is a ALU which works, that is a perform arithmetic operations. Then again we will access memory so that we can store those values that are we got from the arithmetic execution, and then we have a write register file phase. So all these phases happens in clock cycle and clock cycles. So to execute one instruction it takes n clock cycles, which is pretty bad because we can do this in one clock cycle if we use a pipeline version. These phases are only being active in a certain period of that n clock cycles, and that's why they are lazy. Like if you see, in other words, all the main units are idle for most of the cycle. So what computer scientists thought that instead of making them idle, why can't we use them simultaneously? So that's how pipeline architecture works. So let's go to the next slide where we will see that how it works. Yes. So now what happens in the processor is this. We have 5 phases. One is the instruction fetch phase. Then we have the instruction decode. Then we have the and then write back. So if you can see here, the instruction fetch phase is basically to take the instruction from the program counter and then it goes to the instruction decode where the instruction is decoded and is stored in the register, and for the operands that we need are taken from the register file, and then it happens in the ALU, the expression, the operation is executed and the values are then fetched to the memory, and then there is a write back that again goes to uses the write register ports to write. So these are the 5 basic phases that happens in a RISC architecture. So yeah, so this is basically an idea of what pipeline is. So before moving forward to types of pipeline which will be taken by years, I just want to give a fact that pipeline is an old concept, but still it is widely adopted in today time also, like in development sector and DevOps. If you see a tool that we all used frequently is a GitHub and GitLab. So there we have a concept known as a CI/CD, that is continuous integration and continuous deployment. So in that paradigm also we use the concept of pipeline. So a pipeline is created in the backend so that all your codes can be pushed and they integrate continuously and deployed on the server. So that means this concept, even though it is very old concept, it is used in variety of fields. So that is why this concept is very important, and it helped us to improve the speed of the processor in the end. So that's why that is a basic understanding of pipeline. So I will, yes, you can take the. This.
Am I audible?
Yes, you're audible.
Yes. So pipelining is basically divided into two types, that is arithmetic pipeline and instruction pipeline. Moving to arithmetic pipeline, and it basically divides an arithmetic problem into various sub-problems for execution in pipeline segments. So it is basically used for the floating point operations and multiplication and various other computation. On the right side, you can see a flow chart of pipeline organization for floating point addition and subtraction. Next slide. So basically, the steps involved in this are comparing the exponents, then align the matrices, then we add or subtract the matrices and normalize the result. Each of these steps take each segment. So the first segment takes care of the comparing exponents, the next, so the segment 2 takes care of aligning the matrices, the segment 3 subtracts the matrices, and the last fourth segment normalizes the result. Next slide. Let's take exponent x and y. So in the first step, we subtract the exponents, then we align the matrices so the y is shifted one place back. Then we add the matrices to store the result in z. Here, as you can see, the result is already normalized, so there is no need for the segment 4. Next slide. So moving on to instruction pipeline. In this, instructions can be executed by overlapping fetch, decode, execute phase of an instruction cycle. So this type of technique is used to increase the throughput of the computer system. Next slide. So an instruction pipeline reads instructions from the memory while previous instructions are being executed in other segments of the pipeline. Thus, we can execute multiple instructions simultaneously. The pipeline will be more efficient if the instruction cycle is divided into segments of equal durations. Okay, next slide. So the general sequence of steps which are used during the execution of an instruction is fetching the instruction, then we decode it, then the effective address is calculated, then the operands are fetched on which the instruction is to be applied, then finally the execution of instruction takes place and the result is stored in the proper place. Next slide. So we will be understanding how the instruction pipeline works with the help of an example. So here the FI denotes the fetch instruction, DA denotes the decode of an instruction, FO denotes the fetch operands, and EX denotes the execution. So in the instruction is fetched on the first clock cycle in segment 1. Then it is decoded in the next clock cycle. Then operands are fetched, and finally the instruction is executed. That here the fetch and decode phase are overlapped due to pipelining. First instruction is being decoded, next instruction is fetched by the pipeline. You can see that it is a branch instruction. Here, when it is being decoded, fourth instruction is fetched simultaneously. But as the third instruction is a branch instruction, it may point to some other instruction when it is decoded. Thus, the fourth instruction is kept on hold until the branch instruction is executed. When it gets executed, then the fourth instruction is copied back and the other phases continue as usual. That's it for the instruction pipeline. Now we'll be moving ahead.
Okay, thank you, Yash. now I'll be talking about pipelining hazards. Now, pipelining is great and all, and from the previous two slides, you can see how influential pipelining has been. But as it is a machine operated, and since pipelining works at the processor level, there will always be conflicts or hazards or some kind of problems that will arise. And in the previous slide, as Yash presented the instruction set pipeline, we saw that there was a stall or there was a break in where after the branching, the instructions didn't execute for some time. Now that is called as a control hazard. As there is a problem in the control flow, because when a control flow, like for example branching or jump statements are executed, the register or the processor does not know where the destination or target address is. So what it will do is that it will not execute the next set of instructions till it finds out the destination address. That's why there was a lag over there, or it's called as a stall. Now in the further slides I will be explaining it. Now hazards that arise in the pipeline prevent the next instruction from executing during its designated clock cycle, that is simultaneous clock cycles. So there are basically three types of hazards: structural hazards, data hazards, and control hazards. The previous one that was because of the hazard that arises due to the branching was known as a control hazard, which causes a delay in fetching of instructions and decisions about changes in control flow. Structural hazards are because there is not enough resources or hardware, for example cache or buffers as such. And data hazards depends upon the prior instruction that has been entered in the pipeline. Now I'll talk a little about structural hazards. As you can see in the figure, in the designated clock cycle, the memory has been accessed as well as memory has been fetched. Now, since there is only one cache for accessing it, it will be considered as a structural hazard. So structural hazards are usually known as resource hazards, because if the computer or processor does not have enough resources to access or to carry out the pipeline instructions, then they would cause a problem and cause a lag or stall inside the pipeline, which would actually affect the processor speed and performance. Now, data hazards. Data hazards occur when there is a data dependency inside the stages of the pipeline. Now, the most common of them all are read after write, that is raw, write after read, and write after write. But the most observed was read after write dependency. So I'll give you an example. Like for example, there's I2 and I1. Now, over here, the first instruction is where R5 and R3 are added, and it's put into stored into R2. And the second instruction is where R2 is added with R3 and stored into R4. But because of pipeline, when I1 is being executed, R2 will also be simultaneously executed. But the values of R5 and R3 are only added, but it has not been saved into R2. And whereas in the second instruction, R2 has already been called. Since the data has not been saved, there will be we won't get the answer of R4. And hence there will be a data dependency between I2 and I1. So this is known as a data.
Arjun, your voice is not audible. Am I audible, guys? So whenever you perform pipelining, there is a possibility of getting hazards. Based on the type of data, you can classify your data hazard as a raw, var, and wow. So when there is a delay,
Again, sorry for the
yes, can you proceed now?
Ma'am, please kindly just give me a minute. Here's the PPT.
Okay. So till now, let me elaborate. So if there is a dependency on data, if your processing is going to wait for the arrival of data, we'll be calling them as a data hazard. Okay, so it's like if you're planning for a movie along with your friends, if your friend is coming late, we have to wait, right? So that is called your stall. Okay, so when there is a delay happens with respect to data, we'll be calling them as a data hazard. Okay, so when a delay happens along with the dependency of your control instructions, we have if for while all these conditional instructions, if the delay happens with respect to those, we'll be calling them as a control hazard. Okay, these hazards will be handled by the architect in different ways. I think this team is taking the lead in presenting those things, and their presentation along with the simulation, actually if it works well, it might be very very useful for you guys to understand it in a better way. So how this pipelining gets executed perfectly. So with pipelining, the performance of the system obviously increases, and without pipelining it may get degraded. So that is all about your pipelining. Even I can say everyone, we are all doing all the pipelining processing. So now I'm doing a live session. I'm keep on interacting through WhatsApp, and meanwhile I'm just working with your chats as well, counting the votes. So these are all, it's your happening at next processing, right? Instead of waiting till the completion of one process, the second process can assume it or resume it. Okay, that is all about pipelining. Jirosh, you are ready?
Yes, ma'am, I will see. I will just connect to my laptop only the presentation.
Okay, you want me to open this drive link and share it here?
Yes, ma'am. That is a video I have linked to my drive. People can watch that video.
Okay. So the video link is posted in the chat box. Let me post it in the WhatsApp as well for better learning. If your team is done, then I can ask the next team to start, Josh.
Ma'am, we have one more topic, the advantage and disadvantage we are taking by Achintya.
Okay.
One thing I have with some of the slides, I can share that Achintya can continue with it, and when Arjun will come back online, he can continue with his topic.
Okay, you proceed. Instead of delaying, waiting for it, let us not stall. Okay, let us not stall. So this is one of the example of data dependency. We are depending on Argentina. He has to join. So we have waited for some time. This is the best example I can say. It's your data dependency.
Is it visible?
Yes, it's visible.
Achintya, do one thing. You start with your topic. It would be better.
Yeah. Okay. I just go to that advantage slide.
Yeah.
Yeah. So hello everyone. So as of now, we all have seen various things related to pipeline, like what a pipeline is, its design and types, and we were going through the hazards. So now comes the advantage and disadvantages. So like first, like before going to the point, I would like to have a look on this like the image that's there, like pipelines and pipelines everywhere. So from that we can guess that there are a lot of advantages of pipeline. So, like coming to the points now, the first advantage, like the instruction throughput increases. So, like the instruction throughput is like the number of instructions upon the total time taken to execute that all. So, as in the pipeline, we can see that multiple instructions are executed simultaneously. Like in the one stage is like the execution is happening, and in the other stage the decoding is happening. So, by that we can say that the throughput increases. And the second advantage is that increase in the number of pipeline stages, increase the number of instructions executed simultaneously. So that's as we have the more number of stages, the more number of operations we can perform on the different type of instructions. So that's the concept here. And it also increases the ALU speed because of the multiple instructions being executed simultaneously. Now the fourth point will be the pipeline CPU works at higher clock frequencies than the RAM. So that's a very good thing, because in generally the RAM has in the older DDR2 modules, we had the frequency of 800 megahertz, the clock frequency, and in the latest ones, in the DDR4s, we have 4200 megahertz. So delivering at that type of clock frequency in the CPU is really a good thing. So yeah, that's the next thing is that the pipeline increases the overall performance of the CPU. That's what I told in the previous point, by increasing the clock frequency, and finally it makes the system very reliable. So that's all with the advantages. Can you move to the next slide? Am I audible?
Yes.
Yeah. Yeah, so coming to the disadvantages, so particularly the pipeline has more advantages compared to the disadvantages. So the only major disadvantage, it makes the processor a little bit of complex, and it's a little bit of costly to manufacture that.
Ma'am, I'm really sorry for the inconvenience, ma'am. Hello, ma'am.
Let's take an
Yes,
example
yes,
on the pipeline
Ajit,
factory.
continue.
Here every worker
Yes,
is
no
working
issues,
on the
no
same
issues,
part, and
proceed.
after 24 hours one
You're
car is
done?
on road. That means throughput is one car per 24 hours.
No, ma'am, Ajit, continue.
Now here, the pipeline model of same car
Yeah, okay. Coming to the disadvantage, yeah, so as I explained the first point, that it makes the processor a little bit of complex. The disadvantage I can say about the pipeline line. And the second one is instruction latency increases in pipeline processors. So because of some hazard, the latency increases for the execution and decoding of some instructions. So that's not a big deal. And the throughput of a pipeline processor is difficult to predict. So that's also related to the hazard. Some hazards we have to stall at some time, and so that's why the throughput is difficult to predict. It depends on the various situations, which type of hazard we are facing. And again, the longer the pipeline, the worse the problem of hazard for branch instruction. So the branch instruction is that during the execution of that instruction, at last we will get to know that the next instruction addresses that. So the longer the pipeline, the later we will get to know that the next instruction that we have to fetch is at which address. So that will be a big problem. If the pipeline will be longer, it will have a more number of stages. Now next comes to that inability to continuously run the pipeline at full speed because of pipelining hazards, which disrupt the smooth execution of the pipeline. So we can't run the pipeline continuously at a full speed because of some hazard, so it creates a roadblock to that. So we have to include some stalls and that, so that a little bit decreases the performance. That's all with the disadvantage. Yeah, can you move to the next slide? Yeah, so in short, if we can summarize summarizing the advantages and disadvantages. So the only major advantage that the pipelining gives us is the performance improvement. So by pipeline instructions, you are able to pump in more instructions, and so you get a significant improvement in processor speed. And this happens because you are able to execute part of instructions in a parallel to parts of other instructions. So that simultaneously executing a lot of instructions. So consider the case when you are trying to execute 3 instructions, let's say. So each of cycle length 3. So in the case of the pipeline execution, you will be able to get them all done in 5 cycles. But if you're executing without pipeline, then it will take for you 9 CPU cycles to complete them all. So yeah, that we can see from that image also, that boy, that thing that the high performance is delivered. So definitely, the performance improvement is a major factor. Now coming to the disadvantage. So the only major disadvantage is that it makes things complex. So a little bit of complexity of the structure arises due to the pipelining concept. Like we have to take care of the branch penalty and forwarding, and it makes things really complex, and several research problems arise as a result of these complexity. So like that's not a big deal. That's why that man is saying that Game Boy pipelines are bad, because like the advantages are so much that it diminishes the disadvantage. So yeah, that's all. Can you move to the next slide? Yeah, so till now we all have gone through all the theoretical concepts. Yeah, this one.
Yeah, continue, Ajitya.
Yeah, okay. So till now, we all have gone through all the theoretical concepts regarding the pipeline. So I would like to finally conclude by giving you all a real-life situation to keep the concept of pipeline live in your mind. So let's have a look at that real-life situation where you can observe the concept of pipeline being followed, and that's none other than the McDonald's drive-through. So as I guess you all are familiar with that. So, like let's say in the McDonald's drive-through we have like 3 counters. Like the first one for placing the order, the second one for doing the payment, and the third one for receiving the order. And so it's like that, let's say at a particular time, like car 1 is placing the order. That at the same time, car 2 had placed the order earlier when the order placing counter was free, like the no other car was there. So that car is now doing the payment. And the car 3 is receiving the order at the same time, because that car has done all the previous options like the giving the order and doing the payment earlier. So as you can see at a particular unit of time, car 1 is placing the order, car 2 is doing the payment, and car 3 is receiving the order. So it's just like the pipeline concept. Like at the same time, an instruction is being fetched, the other is being decoded, and the other is like, let's say, written back to the memory. So we can see this my real life situation. And I also said that like what she's interacting with the students here in the Google Meet, and at the same time she's also interacting with the students through the WhatsApp. So that's in that situation also we can see the concept of pipeline being applied. Yeah, so that's all.
Yeah, thank you, Ajitya. I would like to talk. Like I was disconnected during the control when I was trying to explain about control hazards. Now I'll just come back to that quickly. So control hazards. So as I said, showed before, as when Yash was presenting, that is when there is branching or jumping or calls that happens, there will be wrong decisions will be taken by the pipeline. So the pipeline will predict what the next instruction would be, but since it won't be the correct instruction, there will be unwanted instructions that will be inserted into the pipeline. So as you can see in the image, BEQ, we all learned what BEQ is, that is branch equal to. So when that instruction has been executed, the processor does not know what the target address is. Okay, so the instructions, since it does not know what the target address or destination address is, there are few instructions that have been inserted into the pipeline, since it cannot predict what the next instruction has become of. So over here you can see that when this happens, 3 clock cycles are wasted. That means there's a 3-stage stall. As you can see from this, it has been skipped 3 cycles, but the cycle has been occurred inside the processor, but only XOR or the 36 instruction has been executed. So this is what you can understand from what a control hazard is. Now, since pipeline is an all concept, we have already come up with solutions to counter it and make it much more efficient and powerful. So the few ways of eliminating these hazards have been listed over here. Now, insert a pipeline bubble whenever a read after write dependency is encoded, guaranteed to increase latency. Okay, now you might ask what a pipeline bubble is. So a pipeline bubble is actually what do you say? It is a stall. It is a man-made stall or artificial stall that is introduced into the instruction pipeline, so that there is a break for the instruction to be completely executed till the next, so that the next instruction can be executed without any problems. So as you can see, as instructions are fetched or control logic, the control logic determines whether a hazard will or could occur. So the processor will start to predict will a hazard occur. If it is true, then the control logic will insert no operations into the pipeline. That means there will be a bubble where no instruction has been executed. And this place, it increases the time, but it also increases the efficiency. If two instructions occur at the same time, but branching or call, that is control hazards occur, then there will be much more problems rather than just taking some time to execute the problems, more efficiently. So, so use over here we have shown to resolve data hazards. We have shown to insert a pipeline bubble. Also, you can use out-of-order execution to potentially prevent the need for pipeline bubbles, and then use operand forwarding to use data from later stages to pipeline. So, data hazards, as I explained before, it is dependent upon the the previous instruction as well. So, if you use operand forwarding from the previous data, then it will make the pipeline instruction execution much more easier. Now, to avoid control hazards, another way is again pipeline bubble. The pipeline bubble is the most efficient way of eliminating any kinds of hazards in pipeline execution, so that it increases the latency. Or use branch prediction. Now, branch prediction is much more recently developed, as in the processor predicts what the next instruction will be, and if it is right, then the pipeline execution will be much faster and efficient. But if it is wrong, then a pipeline bubble will be inserted, so that the next, even though a wrong instruction was predicted, there will be a gap, so that the next correct instruction can be executed properly. Now, advantages of pipelining and disadvantages was explained by Achintya, and we saw a real life situation as well. Now, these are a few formulas that were found in, that is used for pipeline problems, so to solve pipeline problems, and we would share it inside the WhatsApp group as such. Now, just to pique your interest, we have a small questionnaire as such. Now, question 1 is that to increase the speed of memory access in pipelining, we make use of, we can just show the answer since there is nobody to answer inside the Gmeet, but the answer is cache. Since cache can reduce the speed of memory access by a factor of 10. Now, the periods of time when the unit is idle is called, we have discussed it in my, what the topic of hazards we have discussed, and that is both stalls and bubbles. The stalls are type of hazards that affect the pipeline system. Now, question 3 is the situation wherein the data of operands are not available. Basically, when data is not available, is data hazard. It's pretty much very simple. That's it for about pipelining. I'm sure that you must have understood the full potential of pipelining, and you understood what the term speed in our team name represents. Thank you so much. Have a great day.
Thank you, team. I'm really happy that you all proved that you are my student, bringing the real time and the layman example, and I think they got a better idea, and you concluded with a quiz as well. Good work. Thank you so much.
Thank you, ma'am.
Thank you, ma'am.
Thank you. Next team.
Thank you, ma'am.
Ma'am, can you present right now?
Yes, dearest.
Ma'am, is my screen visible?
Yes, it's visible.
Okay, so basically our topic is external storage systems, and we are going to talk about the optical and magnetic systems. The team is ARC21 and I'm Navya and my team member is Sujana Ray. So basically the secondary or external memory, it is used to store data permanently, unlike the primary memory, and according to the memory hierarchy, it is slower than primary memory in terms of accessing data. External memory is usually used in data transfers and also used for backup. So we are going to talk about two types of systems here, the optical and the magnetic one. Coming to optical disks, as the name suggests, optical, light is used to store data. Here, a laser beam is usually used as the source of light. So basically what is done to store data onto the disk, which consists of spiral tracks, is that it creates dots or pits which form patterns. These patterns represents the data, and this is what we call burning data onto the disk. To read the data, the laser beam is reflected back by the surface of the disk, which is this reflective surface as shown here. And when the beam hits the pit, the reflection is different from when it hits the surface without a pit. So that's how the data is read on a disk. So these are the types of read-only optical disks. The read-only optical disks cannot be altered after they are manufactured. Only at manufacturing time the data is written onto the disks. So these types are CD-ROM and DVD-ROM. The CD-ROM is the compact disk read-only memory. It can hold around 700 to 800 MB of data. And DVD-ROM can hold up to 4.7 GB of data, so it has more space than CD-ROM, and both of these are random access devices. Another disk is the high capacity optical disks, which is the Blu-ray. It can store up to 25 to 50 GB of data, and the dual layered Blu-ray disks can store twice of that. It is also a random access device. But unlike CD and DVDs, the blue light is used instead of the red light. Due to the shorter wavelength of the blue light, it allows for storing more data. The recordable optical disks, in this, the data can be written onto them by computers, which have special disk drives called the burning disk drive. And we have the CD-R and DVD-R, which are the CD recordable and DVD recordable. We can burn data onto these disks, but these cannot be erased. That means we can fill the disk with data, but it cannot be reused after that. But unlike CD-R and DVD-R, CD rewritable and DVD rewritable, these can be reused, as we can erase the data and rewrite onto them. Then we have DVD RAM, the DVD random access memory. These disks are like rewritable DVDs and have similar 4.7 GB of space available. And these are random access devices, but the quality provided is better and of higher quality than DVD RW. So it is usually used in archiving and backups, and also it is used for cam recorders. Sujana is going to explain the magnetic storage devices.
Yes, ma'am. So the magnetic storage or the magnetic recording is for storing data in on a magnetized medium. They use various patterns of magnetization of the material to store the data and is a non-volatile memory. The information can be accessed by using one or more read or write heads. The primary magnetic storage media is the magnetic disk, which uses a magnetization process to write, rewrite, and the access of data. It is covered with magnetic coating and stores the data in forms of tracks, spots, and sectors. Here, the tracks are basically the disk surfaces, which are divided into concentric circles, and the thinner the tracks are, more is the storage.
While the smaller the spots are, the more bits per inch, which also helps in greater storage. The sectors are basically the tracks which are divided where a block of data can be read or write at one time. Next is why we use magnets. Because magnets are readily available and it's cheap and they can be formed into many shapes, and we can work with various sizes, and smaller the sizes, the more the portability, and they can also hold the state, which is very required for storage of data very extremely well. So we can say that they help in reading and writing of data very quickly at a very reliable cost. Next slide. Yeah. So the making of the magnets are basically done by a ferromagnetic material which can be magnetized by exposing to the magnetic field, and this magnetic field is emitted, which can be used for reading of data. And when the magnet moment is aligned, it becomes a permanent magnet divided into two poles, north and south poles, and this helps in the access, writing and reading data by emitting the field. Next slide. Yes, so the working of the magnetic disc. The magnetic discs are basically very thin micrometers size, and they are referred to as magnetic domains. The read and write head is used to detect and modify the material by magnetization, and we use a polycrystalline natured material which have very few hundred magnetic grains. Now we come to the magnetic recording classes, which are divided into the analog recording, which is based on the fact that the remnant magnetization of a material depends on the magnitude of the applied field. The magnetic material is normally in the form of tape. With the tape in its blank, it's initially demagnetized. When recording, the tape runs at a constant speed, and the writing head then magnetizes the tape with current proportion of the signal. Next comes the digital recording. Unlike the analog recording, instead of magnetic distribution, the digital recording needs two stable magnetic states, which are the plus ends and the minus ends. And they are done on a hysteresis loop. The best examples of digital recording are floppy disk and hard disk drives. Third one is the magneto-optical recording. The magneto-optical recording reads and writes data optically by the use of laser, and the magnetic medium is heated locally, which then induces a rapid decrease of the coercive field. And the lastly is the domain propagation memory. The domain propagation memory is also called the double memory. The basic idea is to control the domain in a magnetic medium such that it is free of any microstructures. Next slide. Yes. Now comes the applications. There are mainly three basic applications of magnetic disks, which are compact disks, floppy disks, and hard disks. Floppy disks are basically floppy disk and hard disk. They are basically divided into tracks, which are further divided into sectors, as I explained. And they both have the read and write heads or arms that are positioned based on the addresses. The floppy disks are also circular in shape, plastic embedded, and millions of elements of magnetic material stored in them. The hard disks are also similar, but they consist of platters holding the magnetic elements. Next is the advantages. Yes, the advantages are basically we can access the data by using magnetic disk very fast almost at a speed of 1000 kb per second, and the data can be read directly from any part of the hard disk. And some magnetic storage devices are also very cheap, and most of them can hold a large amount of data. While there are a few disadvantages of magnetic disks too, the disadvantage being that the data can be altered very easily because of a change in magnetic fields and mechanical problems, and gradually there's a loss of charge which results in the data lost, and the hard disk eventually also fails with which stops the computer from working, and the regular crashes and damages can lead to loss of data in that sector. The disk is also fixed inside the computer, cannot be easily transferable, so they are not very portable and the mobility is very less for magnetic disk. Thank you, ma'am. That's all for our presentation.
Thank you, dears, explaining about the magnetic disk. Thank you so much. Next team, who is ready?
Ma'am, can I present?
Yes, Sahil.
Ma'am, are you able to see my screen?
Yes, Sahil, I could see.
Yeah, good morning, Maheshwari ma'am and one and all present here. So today I am going to present in front of you a simulation project which I have done using the eSync tool. So the circuit which I made is the negative diode clipper circuit. So my team name is Team SF and my team code is ARC18. So first of all, what's a diode clipper circuit? So diode clipper circuit is basically a wave shaping circuit which takes an input waveform and clips or cuts off its top half or bottom half or both the halves together depending upon whether it's positive diode clipper or negative diode clipper. So the clipping of the input signal produces an output waveform that's a flattened version of the input. So that's why it's also called as diode limiter. For example, we can say that half-wave rectifier is a clipper circuit since all the voltages below 0 are eliminated. Now, what's the basic principle behind the working? So when a diode is forward biased, it allows currents to pass through itself, clamping the voltage or like clipping the voltage. When the diode is reverse biased, no current flows through it, and the voltage across its terminals is unaffected. So this is when it's reverse biased, no current flows through it, and the voltage across its terminals is unaffected. And this is the basic operation of the diode clipping circuit. So how the negative diode clipper works actually? So negative diode clipper it's a type of shunt parallel clipper. So it's called like that because the diode is connected to the output side and the resistance is connected at the input side. So it's called parallel because the output is developed parallel to the diode. In negative clipper circuit, the diode is forward biased during the negative cycle of the sinusoidal waveform, which I am giving as input, and limits the voltage as the diode acts as short circuit, and there is no voltage in case of short circuit. So while during the positive cycle, the diode will be reverse biased, so it acts as open circuit, and the output voltage will be equal to the input voltage. Then the waveform will be passing unaltered without any changes. But depending upon the value of voltage and the resistance we provide, we can see some portion of the positive waveform also getting reduced. Here we can see the negative cycle clipped off as a result of this. As the diode limits the negative half cycle of the input voltage, it's called negative clipper circuit. So this is basically the circuit diagram of a shunt parallel negative clipper. You can see the input waveform and how the negative portion gets chopped off or gets limited. And I have also shown one oscilloscope output. The yellow color waveform is the input waveform, and the blue colored one is the output that we are getting after passing through the negative diode clipper. So the schematic diagram. The components I've used is diode, resistors 110 ohm and 100 ohm, connection wires, power flag, ground supply, sine power supply, and labels. This is the schematic diagram which I have made. This is the negative parallel shunt diode clipper. So you can see the power flag is connected to give supply to the ground supply, and the sine power supply, then the labels V in and V out. Then I used two resistors, 10 k ohm in the input side, and in the output side I have used the 100 k ohm, 100 kilo ohm resistor. So coming to the simulation results which I obtained First of all, ngSpice plot which I have obtained. So you can see the input waveform which I have given to the circuit, and this is the ngSpice output plot which you can see the negative portion clipped off or chopped off. And get it, here you can see it was somewhere around -10, and here it's like between 0 and -1, the voltage. So the next one is Python plot which I have got. The Python plots, you can see the Python input plot, as I said, is the input plot, and not the voltage, it will be from 0 to plus 10 volts and negative 10 volts. I will use the amplitude voltage as 10 volt and the frequency as 50 hertz. This is the Python output plot. Here you can clearly see it's between 0 and -1 and not up to -10. And here also you can see some clipping has happened in the positive side also because of the resistance and voltage vary. It keeps on varying. And this is the combined input and output plot for your clear visualization. You can clearly see the red line and the blue line where the chop of the clipping has happened. And this is the current versus time plot which I have obtained in the circuit. And now coming to the practical applications. So the diode clipping circuits are usually used in voltage limiting applications and in separation of synchronizing signals existing from composite color picture signals are also used in past times. And clippers, they are also used in transistors to protecting the transistors from transient effects by connecting the diodes in parallel to the inductive load. And in case of generating new waveforms or shaping the existing older waveforms, and frequently using FM transmitters for removing excess ripples and signals above a certain noise level. These are all the possible practical applications of the negative diode clipper circuit. And the main difference between the positive diode clipper circuit and negative diode clipper circuit is the polarity of the diodes. It's just the reverse of the negative diode clipper circuit. Now I'm concluding my presentation. Thank you.
Thank you so much, Sahil. Sahil, is it you, the SF team name?
Yes, ma'am.
Before you presented, many of your friends started voting your number with ARC18, and I could see SF also got voted earlier itself. I think you have lots of fans and friends. Keep going. Thank you for your presentation. Thank you, Fazil.
Can you present it?
Yes, Arvind, you can.
This is team 19.
Yes, dear, tell me.
Can we go next?
Next, after Arvind, can you proceed?
All right.
Thank you, dear.
Yes, ma'am. 1 minute. Ma'am, are you able to see, ma'am?
Hey
Yes,
guys, welcome to
I could
ARC,
see.
and we are team member ARC22, and we are going to speak up on the topic external storage management system, and our team is 86. And this team is an x86 is an Intel ARC-based architecture, which was the most successful architecture of Intel, and over to Mahesh.
Next slide, please. Our team members are myself, Mahesh, along with Neha, Arvinda, and Prasanna, here to take you through this journey. Next slide. So we are now going to look at the topic called as external storage system. What comes to mind on hearing this word? You would remember that once upon a time when you were using this big bulky computer, you would have something called as a floppy disk, which again, fun fact, is what the save icon in Word, among others. So this is basically used to store when you have a computer, you might have in those days had limited memory. So, we use something called as external, all named as V series, and now we are using more advanced such as SD cards and hard drives. And these are again removable or non-removable, temporary or permanent, and accessible over wire or wireless network. Next slide. So again, what is the major advantage in using external storage system? It is that it can be transported anywhere easily since it is not a part of a computer. It can be carried from one computer to another computer, which was extremely helpful in those olden days, and it is also even relevant now with the advancement in external storage system. And it serves as a backup to a primary storage and can be again useful for transferring data from one computer to another also. Next slide. This is also really important since cost related to external storage systems are very low, and storage capacity for a computer, laptop, or in these modern days, smartphone also increases multifold thanks to external storage system. Below is a picture again showing how in this time, that is 2020, how which are the major companies producing these storage systems, and those are Dell Technologies, Hewlett Packard, Hitachi, IBM, NetApp, along with the rest of the market. And you can see that Dell Technology is the major producer of external storage system. Now over to Arvind.
Now I'm going to explain the different types of external storage system. One is the magnetic storage, second is the optical, and third is the flash memory devices. Now we are going to see about the magnetic storage system. As the name suggests, magnetic storage system, it uses magnetic tape used for digital recording, and it stores the information as in the tape. And in previous years, it was used open reels for recording in the data, and now it has been converted to magnetic storage. As you can see the pictures over here, there are the pictures of the hard disk. There are a few examples of hard disk which we use in the computer. And next thing I'm going to say is optical storage. Optical storage uses the laser technology for the data storage and retrieval, and it is the most faster when compared to the magnetic storage system. And a few of the common optical storages are CD-ROM and the compact disk, which we use in our systems, and it is most powerful when compared to the magnetic storage. And next, I'm going to explain about the flash memory devices. So flash memory devices, in particularly, they're used for semiconductor memory, but now it's been widely used, and it is a popular storage medium, and it is of two types, that is AND flash memory and NOR flash memory. As mentioned, flash memory can be seen in variety of forms, and it is used in SD cards, in cameras, and also in phones, which we use. The SD cards which we use in the phones are also based on the flash memory devices, and as the image suggested, we could see. So we are going to see the application and the demonstration of hard drive. So this is the computer hard drive, and we link this in the chat box so that you can have a full video of what is happening over here. So over to me.
Yeah, now I'm going to explain about the architecture of a hard disk. This is a basic structure of the hard disk. This has a main spindle and a head and a side, and there are many platters, and there is an arm and head stack assembly, as you can see here. And an external storage system or a storage controller is a device that coordinates and controls the operation of one or more disk drives. A storage system synchronizes the operation of the drives with the operation of the system as a whole. The system can manage a combination of internal and external storage and represent all the detected storage as MDisk. So the hard disk consists of many number of platters. The platters can rotate in a very high speed, like say 5,400 revolutions per minute to 10,000 revolutions per minute. The disk head can move over the platter surface for reading or writing the data bits. The disk head can only read or write the data when it is on the desired disk surface area. Can you move next? Yeah, the data access time of data on the disk consists of three things. The first one is the seek time, which gets to the write track. And the second is the latency, which waits for the right sector to rotate under the disk head. And the third is the transfer time, which is actually the reading of the data. Yeah. The each platter is logically divided into many number of tracks, and each track is logically divided into number of sectors, and the sector is uniquely identified by its sector number. The disk sectors are usually of 512 bits in size. To facilitate the data access, the number of sectors are logically grouped into the disk block, and each disk block contains many number of sections, and each section is identified by its sector number, and each disk block is uniquely identified by its block number. Disk blocks are usually of 4K or 8K bytes in size. The sectors of a disk block need not to be located contiguously or on the platter. Now over to Prasanna.
Yeah. So now we have seen the structure of the hard disk. So we'll see how file organization is being done in the hard disk. So big companies like Microsoft and the parent company of Linux use file systems differently. The Windows Microsoft, what they use is that they use FAT32 and NTFS for the file system handling. And the Unix, the parent company of Linux, uses UFS and ZFS, the UFS file system and ZFS file system. So if we have some hard disk space of, let's say, some XGB, not all of the XGB is actually devoted for storing data. Some amount of the data is actually stored, which stores the location of the data stored. And these are called as directory disk blocks. They contain a large number of directory entries. Next slide, please. And yeah, so the directory block, with the directory block, we can know that where the file is located. So a file can be uniquely identified by its file name. Always a file name for a non-empty file. It is always unique. With the help of that only we can open a file. And you can access the file by the open file command, which says to open the file. We have different commands like write a file, read a file, and append a file like that. We use open file in order to open it. And this operation locates the directory entry of the file and obtain its disk blocks of the file. Yeah, thank you. And we have a quiz. I hope you all attend that, and it's a very nice quiz. And the sixth question is the best question. Thank you.
So thank you for all. Hope you understood and fasten as usual, and we'll have conduct a quiz. Thank you.
Thank you.
Thank you, team. Are you going to show the Kahoot here?
Yes, ma'am. I'll be.
Okay.
Yes, ma'am.
Ma'am, you could also participate.
Sure, I'll participate.
Yes. And also the other participants and attendees who are presenting also could also attend the quiz. It would be great.
1 second, ma'am. I'll just start it.
There will be 6 questions.
Before starting, could you give the instructions?
There are 6 questions and you need to answer them. First question is over. The time over here, only 7 seconds.
Hey, again and again it's asking for the pin. It's not allowing to enter into the quiz.
Okay, so I actually started it, ma'am. So
Okay. Then proceed. No, proceed.
This is the correct answer.
More time was given for the questions. Wrong answer.
You are correct. Take. So this is the last question.
A bonus question.
This is just a fun question. So yes, ma'am.
Yes, very good. Good try. You would have waited for a few more minutes, Prasanna, so that some of might join. Even it took time for me to join, right? Okay, no problem. Good try. Thank you so much.
Yes, ma'am. If possible, I think so we could conduct tomorrow.
Yes, even we can conduct it later on also. Okay.
Yes.
Fine.
Thank you. So participants are less, I guess.
Yes. Thank you.
Yes.
Even you started immediately. I talked from the window. I just start trying it, but it not allowed me to start it. No problem. We'll do it later. Okay.
We'll do it later.
Sorry.
Yes.
Okay, no problem. Bye. Next team.
Thank you, ma'am.
Team 19.
Yes, proceed, Dakshina.
Yes, ma'am.
Good morning, everyone. We are team ARC19, and today we are going to discuss about the topic magnetic disks. Next slide. Memory is the medium by which data is stored and manipulated. In computer systems today, there are two types of memory, internal memory and external memory. Internal memory is associated with RAM or random access memory and is also known as main memory. It is smaller in size but has faster access times. External memory is also known as secondary memory. It is separate from main memory and is in the form of magnetic disks and external drives which have much higher memory capacities. Next slide. In computing, external storage comprises of devices that store information outside the computer. Such devices may be permanently attached to the computer, may be removable, or may use removable media. Next slide. There are many types of external storage. Some examples of forms of external storage are CDs, DVDs, external hard drives, flash drives, PC cards, and online or cloud storage. Next slide. Now we are going to talk more about the magnetic disk. A magnetic disk is a storage device that uses a magnetization process to write, rewrite, and access data. Data is represented on a circular surface called a platter. Platters are covered with a magnetic coating and store data in the form of tracks, spots, and sectors. Next slide. Some examples of magnetic disks include hard disks, zip disks, and floppy disks. Next slide. A magnetic disk primarily consists of a rotating magnetic surface called platter and a mechanical arm called spindle or shaft that moves over it. Platters are stacked on top of each other on this single rotating device. Together they form a comb-like structure. The distance between platters is large enough to mount a read-write disk head on a pivoting arm. There is one read-write head per surface or platter. All arms are mounted rigidly on the same shaft. So this mechanical arm is used to read from and write to the disk, and this is done using a magnetization process. The disk is coated with a non-magnetic material called the substrate. They are also coated with a magnetic material such as iron oxide. There are two types of coating: hard disk made of rigid aluminum and one made of flexible plastic. Traditionally, the substrate has been an aluminum or aluminum alloy material, but more recently, glass substrates have been introduced. Next slide. Magnetic disks made of aluminum alloys are used in hard disk drives or HDDs because aluminum is non-magnetic, lightweight, and grindable. Aluminum substrates are also less expensive than glass substrates. Next slide. The following are the advantages of glass substrate coating. There is an improvement in the uniformity of the magnetic film surface to increase disk reliability, a significant reduction in overall surface defects to help reduce read and write errors, and a greater ability to withstand damage and also improved shock resistance and overall higher stability. Next slide. Data are recorded on and later retrieved from the disk via a conducting coil named the head. There are two types of head: read and write head. During a read or write operation, the head is stationary while the platter rotates beneath it. Next slide. Now we're going to talk about the write and read mechanism. So first, the write mechanism. It is based on the fact that electricity flowing through a coil produces a magnetic field. Electric pulses are sent to the write head, and the resulting magnetic patterns are recorded on the surface below, with different patterns for positive and negative currents. And then moving on to the read mechanism. The read mechanism is based on the fact that the magnetic field moving relative to a coil produces an electric current in the coil. When the surface of the disk passes under the read head, it generates a current of the same polarity as the one already recorded. Next slide. And this is the structure of the head and the recording surface below the head, and how the coil is set up to read from and write to the surface below. Next slide. The read head consists of a partially shielded magneto-resistive sensor, otherwise known as MR sensor. The MR material has an electric resistance that depends on the direction of the magnetization of the medium moving under it. Next slide. Now it's about the head. The head is a relatively small device capable of reading from or writing to a portion of the platter rotating beneath it. This gives rise to the organization of data on the platter in a concentric set of rings called tracks. There are thousands of tracks per surface. Next slide. So this is the structure of the disk data layout. The data is organized on the disk in the form of a number of pie-shaped sectors and tracks. The tracks are divided into sectors that contain blocks of data. All read and write operations on the magnetic disks are performed on the sectors. The floating heads require very precise control to read or write data. Each track is the same width as the head, and the head needs to locate sector positions within a track. It's required to know the starting point on the track and end of each sector. To perform this, the following needs to be done. First, the location data needs to be recorded on the disk, and the disk needs to be formatted with extra data. Next slide. The adjacent tracks are separated by gaps known as intersector gaps in order to prevent misalignment of the head and magnetic field interference. Data are transferred to and from the disk in sectors. There are hundreds of sectors per track, and these may be of either fixed or variable length. Nowadays, 512 bytes is the universal sector size. Next slide. The information can then be scanned at the same rate by rotating the disk at a fixed speed known as the constant angular velocity. Next slide. Now we'll be seeing the advantages and disadvantages of constant angular velocity or CAV. The advantage of using CAV is that the individual blocks of data can be directly addressed by track and sector. The disadvantage of CAV is that the amount of data that can be stored on the long outer tracks is the same as what can be stored on the short inner tracks. To increase density, modern hard disk systems use a technique known as multiple zone recording, in which the surface is divided into a number of concentric zones. Within a zone, the number of bits per track is constant. Now, Dakshina will continue to explain more about the magnetic disk, starting with the physical characteristics of its head.
So there are many types of heads, and one of them is fixed head disk and movable head disk. And here only one read-write head is present per track, and all of the heads are mounted on a rigid arm that extends across all tracks. Because of it, it should be positioned above any track, so the arm can be extended for this purpose. Whereas in a non-removable disk, it's permanently mounted in the disk drive. And the hard disk in a personal computer is an example of non-removable disk. A removable disk can be removed and replaced with another disk. And for the most disks, the magnetizable coating is applied to both sides of the platter, which is called as double-sided disks. But they're quite expensive, so mostly single-sided disks are used. And now we're going to discuss about the multiple platters in a disk. So we know that a magnetic disk is made up of one or more platters in the form of disk covered with magnetic media. Each platter has two working surfaces that stores data. Digital information is stored on magnetic disk in the form of microscopically small magnetic needles. All of the heads are mechanically fixed so that all are the same distance from the center of the disk and move together. And this is the physical representation of multiple platters in a disk. And the platter keeps spinning at high speed while the head of the arm moves across the surface and floats on a thin film of air. So when a small current is applied to the head, tiny spots on the disk surface are magnetized and data is stored. When a small current is applied to those tiny spots on the platter, the head reads the data from the disk. And now we're going to look into the track and cylinder structure of a magnetic disk. The set of all tracks in the same relative positions of the platter is referred to as a cylinder. The number of cylinders of a disk drive is exactly equal to the number of tracks on a single surface in a drive. Track number on each platter is also the same, whereas cylinders are vertically formed by tracks, and this mechanism is used by the floppy disk, which is a small flexible platter, and it's the least expensive type of disk. And this is the physical structure of the cylinder in a magnetic disk. Early devices lacked the precision and allowed only a certain number of tracks to be placed in each disk. Greater the precision of the heads, they allowed a greater number of tracks to be closely packed together in subsequent devices. And therefore, RAID, which is redundant array of inexpensive disks, was introduced. So RAID, which is a data storage virtualization technology, works by placing data on multiple disks and follows input-output operations to overlap and therefore improves performance. Because of the use of multiple disks, it increases the mean time between failures, and storing data redundantly also increases fault tolerance. So RAID is a form of redundancy used to deal with hard disk failure. RAID arrays are treated as a single logical drive by the operating system. RAID employs the techniques of disk mirroring and disk stripping. Mirroring will copy identical data onto more than one drive, and these partitions help spread data over multiple disk drives. Each drive storage space is divided into units ranging from a sector of 512 bytes up to 7 megabytes. And so there are 7 different types of hardware RAID implementation. They're labeled as RAID 0, RAID 1, and the last level, that's the 7th level, is RAID 10. Usually the 0th, 1st, and 3rd levels is used for high transfer rates, and the 4th, 5th, and 6th is used for high transaction rates. So now we're going to look more into the different levels of RAID. So RAID 0 uses disk stripping, in which the data is divided into blocks and spreads them across multiple physical disks. Because RAID 0 makes good use of multiple disks, it tends to improve read and write performance. RAID 1, which also uses disk mirroring, maintains a complete copy of the data on a second separate physical drive. And RAID 1 provides fault tolerance and overall improves the read performance. RAID 2 spreads both data and parity information across multiple physical disks, and And like RAID 2, RAID 3 implements data stripping, but unlike RAID 2, RAID 3 maintains all binary information on one disk for a better performance. And RAID 4 uses the same data stripping methodology as RAID 2 and RAID 3, but provides better performance by using a larger disk. And RAID 5 also uses data stripping method, which is similar to RAID 0, but adds parity to the data stripping and therefore has a better fault tolerance. And at last, we have RAID 10, which is a combination of both RAID 1 and RAID 0, uses a stripped array of disks like RAID 0, but fully mirrors a stripped data set, which is similar to that of RAID 1. RAID 10's use of multiple disks gives you the best performance of all RAID levels, but it can be quite expensive. And so to conclude, in RAID technology, data are distributed, that is, it enables simultaneous access from multiple drives, and the concept of parallelism is used throughout the computation. Separate input-output requests can be handled in parallel, and thereby improving the overall input-output performance. Thank you.
Thank you so much, Ria. Thank you for your participation. I think everyone is done.
We're the only one in the meeting.
Okay, dear. Thank you so much. Bye-bye. So, thank you so much for everyone who participated here. Today, the session was really good. We had a mixed flavor of... Thank you all for your real participation. Today, we had a mixed flavor of magnetic disk. We have touched upon all the magnetic disk external memories. Even we touched upon the right technologies. They have presented something on pipelining, the corresponding hazards. Then parallel and distributed computing has happened here. And even quizzes has been conducted, and some team has projected the eSIM project as well. So we'll stay tuned. We'll see tomorrow. Thank you so much. Bye-bye.